Okay, let's get started. You'll remember from last time we played the little cartoon game where I showed you two cartoons and asked you to spot the difference. Let's play that game again this morning. Last time you checked the schedule, there is one difference compared to this morning. Just one, not 14 this time. What is it?
Beautiful evidence.
What's that?
Beautiful evidence.
Yes, that's a recent change, but the most recent change as of 5 minutes ago is I pushed back the submission deadline for Deliverable 3. It's now due tonight at 11:59 p.m. The reason why is load and save with NumPy. How many people wrestled with saving and loading with NumPy? Some yes, some no. Okay, that's what I thought. If you've already submitted Deliverable 3 and everything works, no problem. If you struggled with Deliverable 3 and had problems with loading and saving data, and you submitted a partially completed Deliverable 3 last night just to make sure that you got it in on time, you got a 24-hour extension. If you want to go back and revisit loading and saving with NumPy, you have until tonight to do so. Yes?
Do you allow for multiple submissions, or do we have to email you?
I've changed the test options so there's now multiple submissions. So you should be able to resubmit Deliverable 3 if you want up to 11:59 p.m. tonight. My apologies, loading and saving works for some platforms and some versions of NumPy and so on. Jack the TA very graciously has gone back and clarified a few things. I put a note about this on Blackboard. Jack changed step number 27, 29, and 30. And if you look carefully, again playing spot the difference game, he's changed one of the arguments for file loading and saving here, which is to add B. What does B stand for? Binary, right? So this just specifies that you're reading and writing binary files. If you remember in Deliverable 3, we started by reading and writing text files so that you could just open it and read that it actually saved the right number in there. So text files are nice because they're human readable. We're going to switch over now to binary files, which you can't open and read, but it makes things easier as we move forward. Yes?
If we did Deliverable 3 and it works and it's all good, do we still need to do the binary change?
You do not. As long as it works, as long as Deliverable 3 works, that's fine. As I mentioned, in a few weeks' time, we're going to collect data files from all of you. So we're going to have a combined training set of the X, Y, and Z coordinates of all of your hands. When we get to that stage, we'll make sure that everybody is saving in the same format so that we can read and write each other's files. But we'll deal with that, I think, in 2 weeks. I think it's Deliverable 5. Any other questions? All good? Okay, I apologize if you had issues with that. I think everything should be clarified now. That's Deliverable 3. As usual, we're going to talk about the new deliverable this morning, Deliverable 4. Deliverable 4 is a little bit different from the other three. This week you're going to be setting your leap motion device aside, and we're going to be developing your machine learning algorithm, which is the K nearest neighbors algorithm, or kNN algorithm. You're going to get that working in Deliverable 4, and then in Deliverable 5, you're going to put leap motion and kNN together again. So you don't need your leap motion device for this week. Okay, so what we're going to do today, I'm going to talk just a little bit about Deliverable 4, but before we talk about Deliverable 4, I'm going to just do a little bit of work on kNN here. How many people have heard or used the K nearest neighbors algorithm before? Very few of you. Okay, that's good. So we'll spend a little bit of time talking about the basics of what it is. We'll go back and then talk about Deliverable 4 and how to implement it. Okay, so machine learning is a huge topic. It's a very hot topic at the moment. There are whole courses here at UVM dedicated, so we're going to spend half an hour talking about just one machine learning algorithm, kNN. I chose kNN because it is the simplest, arguably the simplest of all machine learning algorithms, which is nice. It means there's relatively little for you to do to set it up and use it. It's also very intuitive. You can kind of understand how it works. The drawback of kNN, because it's simple, there's a cost, obviously, to simplicity, which is it's a weak learner. It doesn't work very well. It works well, better than chance, but not as well as some more powerful machine learning algorithms like deep learning and some of the other things you might have heard of. So, easy to implement, but in the weeks to come, when you start to use kNN, it's not always going to work great. You may be signing the ASL number 0 perfectly fine, and kNN says that's obviously an 8, right? And vice versa. Okay. Just keep that in mind. That's not going to count against you. We're not going to dock any grades because your kNN algorithm doesn't perfectly predict every digit. We know that it won't do so. However, you are going to prove that it does pretty well. So what do we mean by pretty well? Pretty well means that it does clearly better than chance, right? So what is chance? Well, if you were to throw up one of the 10 digits, and I'm a pretty weak learner, the worst thing I can do is say, I don't know anything, I'm just going to randomly pick a digit between 0 and 9 and hope that that's the digit that you're signing, right? That's chance. What is the chance? What is the chance that the chance algorithm will get the digit correct? If you put up one of the 10 and it guesses randomly 10%, right? So you're going to prove to us by the end of Deliverable 4 that your kNN algorithm is doing way better than 10%, but I guarantee you it's not going to get 100%, okay? So there's a particular percentage prediction accuracy that you're aiming for at the end of Deliverable 10, and that's outlined in there, but just to keep that in mind. So far, so good? Okay, so let's talk a little bit about the kNN algorithm. And we're going to start today explaining this with flowers. There is a very famous data set in machine learning called the iris data set. This data set is made up of a bunch of numbers that were collected from 150 actual iris flowers. And we're going to do some work here in the spreadsheet today. You can note this down as we go if you like. I'm also recording the lecture, so it'll all be there as well. Okay, so decades ago, a botanist went out in the field and collected 150 irises. And then for each of those 150 flowers, the botanist literally measured 4 features of each flower: sepal length, sepal width, petal length, and petal width. You all know what petals are. Don't ask me what sepals are. I have absolutely no idea. Okay. If you're taking a plant and soil science class, please ask your instructor and please tell me. Okay. For each flower, they measured these 4 features, and they measured them in centimeters. So I'm, again, not a botanist, so I'm just going to pick some numbers here. It doesn't really matter too much. So we have 4 measurements for each flower. And then the botanist took that particular flower and mentioned these are irises. And irises have a number of species. And in this case, there are 3 possible species that flower could be. We're not going to write in the name of the species. Instead, we're going to write a number 0, 1, or 2, which indicates that particular flower belonged to the first, second, or third species. So I'm, again, making up numbers here, but let's imagine flower number 1 had these particular measurements, and the botanist said this particular flower belongs to the second species. So 1. So far, so good? Okay, I'm not going to type in all 150 flowers, but let's type in a few more. They picked a second flower. They measured a few values for this. And it turns out in this case, the second flower belonged to the third species. We'll do one more. Picked a third flower. How's my random number generating going? Okay, let's say this one belonged to the first species, and so on, and they did this for 150 flowers. Okay, so that is exactly that's the shape of the iris data set, very famous in machine learning. It's not a huge data set. How many numbers are in the iris data set? 750? Okay, it's too early in the morning for me. I'll trust your math. Good enough. Not a very big data set, one of the very original ones. The data sets that are used to train deep learners these days have billions and trillions of numbers in them. We're going to start simple and we're going to start small today. So in Deliverable 4, let's jump to Deliverable 4 for a moment. In Deliverable 4, we're going to be actually working with this actual data set, the iris data set, which comes along with a new Python library that we're going to be using today, which is scikit-learn. Inside of scikit-learn, inside this library, there are a number of machine learning algorithms, including kNN. And there are also a number of data sets that come along with it. The iris data set is one of them. Okay, so just to refresh our memory, as I mentioned, we're going to be working with a number of Python libraries in this class. You're all now pretty familiar with matplotlib. Last week we introduced NumericalPy or NumPy, which allows you to slice and dice matrices and vectors. And this week you're going to be working with Scientific Toolkit machine learning in this case. Okay. So, in most machine learning algorithms, we're trying to take the features of certain objects, in this case flowers, and infer or derive a function that will take as input the features of a particular object, let's say flower 2, for example. We take the features of flower 2, we feed that as input to our machine learning algorithm, and our machine learning algorithm outputs a prediction, which is the guess about the class or label of that data set. So there's a lot of terminology in machine learning. Class or label means what set does that particular object belong to? In this case, it belongs to the third set. So far, so good? Okay. I haven't talked about kNN yet. When you start to train your kNN algorithm, how do we know how well it's doing? As we were just mentioning before, it's going to make a whole bunch of predictions, and we're going to see how many of those predictions are correct. You would expect when we apply the kNN to your ASL digits, when there's 10 different digits, it's going to do way better than 10%, but probably not 100%. Okay. So, just to introduce a little bit more terminology, in most machine learning algorithms, we take a subset of the data, like, for example, every odd-numbered row here. So we're going to take the first flower, the third flower, the fifth flower, the seventh flower, and so on. That's going to be our training set. So we're going to train our machine learning algorithm on that training set. So it's going to get better and better. And we're giving our machine learning algorithm the answers for those training instances, right? So for the odd-numbered flowers here, we're going to tell the machine learning algorithm what the species actually is. So this is like you taking a math class and you have a textbook for that math class. There's a number of problems in the book, and at the back of the book are the answers, right? So you do the problem, like the kNN is going to do in a moment. It produces its prediction, which is going to be 0, 1, or 2, and then the kNN algorithm flips to the back of the book and checks to see whether it was right or wrong. If it was wrong, it'll modify its learning. If it's right, it will carry on, and so forth. Okay, that's the procedure, which we'll talk about in a moment. That's the training set. We then take the test set, which is going to be another subset of the data, a non-overlapping subset of the data, right? So we're going to take now flowers that our machine learning algorithm has never seen, which in this example is going to be all the even-numbered flowers now, 2, 4, 6, 8, and so on. We're going to give the input to, we're going to give the kNN learner the 4 features of each of these even-numbered flowers, but we are not going to give it the answer. So this is like if you've now taken the math class and you go and take the final exam, you now see a bunch of problems that you've probably never seen before. A non-overlapping set of math problems. They don't overlap with the problems in your textbook, and the instructor does not give you the answers to the final exam. You write down your answers, and then when you're done, or when kNN is done, we see how many of those answers are correct, and that's how well it does, right? You get a % grade on your final exam. We're going to do exactly the same thing with our kNN learner. So far, so good? If it gets low %, that means that it didn't learn anything. If it gets a high % on the test set, it's working, right? All the excitement at the moment about deep learning is because about 10 years ago now, on most state-of-the-art data sets, most state-of-the-art machine learning algorithms, they would get between 80 and 90% on certain data sets, and for 20 years up to that point, no one had done better than about 80 or 90%. And then back in 2006, Jeff Hinton and some of his colleagues presented a paper of a new machine learning algorithm, a deep learning algorithm that got 98, 99% suddenly in 1 year. That's where all the excitement started 10 years ago, and now everybody knows about it. So that's sort of where the origin of the excitement about AI and robotics started with, which is demonstrating a new machine learning algorithm that did much better than the state-of-the-art at the time. Okay, kNN is definitely not a deep learner. It's not very powerful, but it's simple. It's easy to understand. In all machine learning algorithms, again, they're trying to transform these features, the input vector that they get, right? So obviously all training sets are not the same. Some have more or less features. In our case, for Deliverable 4, we've got 4 features. Machine learning algorithm takes in those 4 numbers and makes a prediction. The trick is, how does it transform those numbers? And there are different general strategies you can imagine, and these are known as inductive biases. So there's sort of the idea behind a particular machine learning algorithm. The inductive bias behind kNN is it's going to assume that flowers that have similar valued features probably belong to the same species. So again, I'm not an expert, I'm not a botanist, but generally speaking, if flower 1 has these particular feature values and belongs to the second species, if there is another flower down here in the set that has values, 4 values that are similar to the values of flower 1, then the bias or the guess is that it probably belongs to the same species. Right? It's kind of intuitive, it makes sense. That's the inductive bias. The question then is, how do we turn that into an algorithm? In kNN, we do that by treating these features as coordinates in an n-dimensional space. So let's focus for a moment on just 2 features, sepal length and sepal width. And I'm now going to switch from the data set here to trying to draw this visually. We have 2 features. So let's label these 2 coordinates as the x is going to be sepal width, and the height is going to be sepal length. Can you in the back see okay? Okay. All right, so now we have just these 2 numbers, so we can take the 2 numbers here and treat them as coordinates in space. So we go along 1.3 along the x-axis and 2.6 along the vertical axis, and we're going to use a circle to represent the second species, so species 1. Okay, let's now visit flower 3. I'm just going to draw points in the training set. We go along to 7.8 and we go up to 8.2, and this one belongs to the first species, and we'll use an X to represent flowers that belong to the first species. Okay, so we could keep going and do this for the 75 flowers that belong to the training set. And I'm not going to draw the third species. I'll just keep it simple like this for now. We'll just assume there's 2 species to keep things really, really simple. Okay, so now for every flower, it becomes a point in a 2-dimensional space. And now let's say I take a new flower. I go out into the field, I pick a new flower. So now we're talking about the test set, and I measure these values. So I go along 2.7, and I go up 0.7, and I land at this particular point here. I'm not a botanist, so I don't know what species this particular flower belongs to. The botanist who labeled the odd-numbered flowers has also left. They're not around. So I'm going to use my kNN algorithm to tell me what species does this particular flower belong to. How do you think the kNN algorithm is going to tell me which species this particular flower belongs to?
It picks K of its nearest neighbors and figures out which type the
majority of them are.
Exactly. So given what I've told you so far, given the name of the algorithm, you can usually figure out what it's going to do now. Given this point, we're going to visit the k nearest neighbors. And in this case, let's set k equal to 4. Why 4? Why 2? Why not 3? Why not 5? I'll come back to that in a moment. Let's just assume we pick 4. So we're here. These two are clearly nearest neighbors. So we're going to take this flower, this flower, this flower, and I think this one is the next closest one. Okay, these are the 4 nearest neighbors to my unknown flower. Which species does this flower belong to? X, right? Again, it's pretty intuitive. We're going to take most of the neighbors, and it turns out flowers that have similar sepal width and sepal length tend to belong to species X. So our kNN algorithm will predict X. So far, so good? That's it, right? Okay, why 3? Why not 5? The answer is, I don't know. And this is one of the dirty little secrets about AI, is in AI there tend to exist for every machine learning algorithm what are known as hyperparameters. Okay? So here are some, the other parameters are things that are kind of already set. So there are 4 features, there are 150 flowers, there are 3 species. So 4, 150, and 3, those are parameters. They're kind of given to us given what we're doing, but then as AI researchers, we can pick new parameters that describe how those parameters are manipulated. Those are the hyperparameters. And in the case of kNN, there's just one hyperparameter, which is k. Okay, so let's think about this. It's hard to pick k, but again, usually you don't want to pick a value that's too low and a value that's too high. What happens if we pick a very low value of k? Let's say k equals 1. What's the problem with k equals 1?
Well, if your dot was kind of in the X cluster, but also closer to like the edge of the cluster,
Yep.
then its nearest neighbor could actually not be an X, it could be an O.
Exactly. So as you can see here when I drew this, actually I made this a pretty hard one, there's sort of regions of X and regions of 0, right? Sort of clusters in this case. For most data sets, if you are able to visualize them, they tend to sort of be clustered, right? So things get tricky when you're on the border between clusters, right? And if k equals 1 is low, and if you tend to be near the interface, you might actually pick up an X where you're actually kind of sitting in the O cluster, but there are no O's nearby, and vice versa. You may be sitting near the X cluster, but it just happens that there's one outlier O that tends to be near you, and you predict O. So things tend to be tricky if you pick k equals 1. Higher values of k sort of recognize that there tends to be noise in the data, right? Things aren't perfect, so we're going to take a sort of majority vote, right? So outliers aren't going to throw us off. Okay, what happens if we pick values of k that are very large? In this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 14 flowers on the board so far. Let's imagine that k equals 14. As big as it can possibly be. What's the problem now?
Then it just assumes that every flower is whatever group is largest.
Exactly, right? So now if I pick a flower here, the nearest neighbors are all the training flowers, right? All the odd-numbered flowers. So the guess is always going to be the majority, which is a tie in this case. Okay, I don't know what kNN does in the case of a tie. Maybe it flips a coin. I don't know. Let's make our lives easier. Okay. So it's always going to predict a circle, right? No matter what flower you pick and what SL and SW equals, kNN just says it's a circle flower, right? No matter what. Which is probably not true, because we know, even in the training set, there's more than one species. So we know kNN has to be wrong as it starts to make more and more predictions. So a value too low is no good, and a value too high is no good. So we want to hit that Goldilocks zone in the middle. But what exactly should it be? Hard to say. what you're going to be doing in Deliverable 2, as you get towards the end of Deliverable 2, is you're going to play with different values of K, and you'll notice how the prediction accuracy on the test set goes up or down. So one of the things you can do is kind of play with that to get a good value of K. Okay. We played this game now using just the first 2 features, but obviously there are additional 4 features. Why didn't I draw on the board using all 4 features?
Put it in the 4th dimension, you can't draw that.
I can't draw in the 4th dimension, right? So the iris data set has 4 features, which means that every flower exists as a point in a 4-dimensional space, which is hard to draw. It is also hard to draw in Matplotlib. So what you are going to do at the beginning of Deliverable 4 is do the same sort of thing that I did here, is you're going to create some new visualizations in Matplotlib using only 2 of the 4 features. Okay. Here are the 75, it should be 75 there, I think, the 75 training flowers. Each dot represents one of the flowers. What do the 3 colors represent? The 3 species, right? So for our purposes, we're going to have red irises, green irises, and blue irises. Given this picture, once you train your kNN learner, which species is it going to have an easier and a harder time predicting? It turns out, as you can see here, that at least for these two of the 4 features we predict here, those 2 features discriminate red irises from the other 2, but those 2 features are not sufficient to discriminate or pull apart the green and the blue irises, right? So again, we can't draw in 4 dimensions, but it's interesting to think about when these points exist, these 75 points exist in 4-dimensional space. There are actually 3 clusters. They tend to cluster together in 4-dimensional space. And when we collapse to 2-dimensional spaces like we do here, easy to predict red, not so easy to predict green and blue. So you're going to create and debug your kNN learner using just the 2 features, and then you can visually see how well you're doing. And then at the end, we're going to turn off Matplotlib. We're going to turn off the visualization. You're going to expand to using all 4 features, and you're going to get back now just one number, which is the prediction accuracy in percent on the other 75 flowers, and we'll see how well you do. Okay. So that's the training set. You're going to be, so this is for the first 2 features. You're going to be submitting in Deliverable 4 not a video this week, but an image, which is the same image for the 2nd and 3rd feature. And that particular picture is not in Deliverable 4. We're going to look at that. We know what that picture looks like. If you submit it and your picture looks like our picture, you're good. Okay? Again, this is for the 1st and 2nd feature. This is just showing the training set. Here's the training set. So the training set circles are circled in black, and I've added in the additional test flowers, the additional 75 flowers. So we've got all 150 flowers here. And you can tell, you can discriminate between the training flowers and the test flowers. And we're using a new visual metaphor here, or we're using a visualization trick to project the predictions of the kNN learner. So we've actually taken the 75 test flowers here. We've gotten back the prediction from the kNN learner, and the prediction is actually visualized in this picture. How? Jack?
Outline of the circle.
The outline of the circle. So the inner coloring of the circles, as you know from the training set, right, is the actual species. Remember that, we know that for both the training and testing flowers. So the inner color is that. The outer color changes on the test flowers, as you can see, right? So again, in visual design, if you do it well, you should be able to figure all this out on your own without me having to tell you. What does the outer color tell you? How do you know how well the kNN learner is doing in this case?
The outer color tells the prediction.
I'm sorry?
The outer color tells the prediction.
The outer color tells you the prediction, that's right. So how well is this kNN learner doing? So. How do you know?
Well, because in the center of the green and blue, there's a lot of mixture of the colors.
There's a lot of mixtures of the colors, right? So you can probably figure out by now, if the inner color is green in this example and the outer color is blue, that means that for this particular flower, the kNN learner got it wrong, right? It predicted blue, but it was actual green. In this case, the flower was actually green, and the learner predicted, the actual flower was blue, it predicted green. So mismatching colors means a wrong prediction. Solid circle means the kNN learner got it right. Do you have a question?
Yeah. Was this model based with only the two features, or did it have all four and then that's it?
Just the two. So it's not doing very well, right? Again, as we saw up here, because blue and green are mixed in 2 dimensions. So it's having a hard time with blue and green, but I don't think there is a single misclassification of a red flower, right? Perfect on all the red flowers, which again makes sense. In lecture 6, which we're going to get to in a few minutes, which is about visual design, this is what visual design is about, right? Trying to create a visualization that helps us understand about what's going on under the hood, right? Whatever that happens to be. In our case, our goal is to try and understand how well our kNN learner is doing. So I created this visualization to help you, as you're creating your kNN learner, know how well it's doing, right? If all you saw were solid colored lines, solid colored dots, you'd know that your kNN learner is doing perfectly, right? 100%. Probably not going to get that. Unfortunately, when we go to using all 4 features, we can't visualize that, but we're using this as a starting point, a scaffold. Get us started. Once we're up and going, we can throw the visualization away and rely on the 4 features. Yes?
Are there some red ones that were wrong?
Remember that the dark outline, the black outline indicates that those are the training flowers, right? So those are the ones that it trained on. So when we're predicting, when we're looking, we want to know how well our kNN learner is doing. We want to see how well it does on the test flowers, which are the ones that don't have a black circle around them, black line around them. Okay. Okay, I think that's all I have to say about Deliverable 4. Any other questions about that? No? Okay, so let's jump back to lecture now. Okay, we are going to finish lecture 5 in a moment, design principles, and then we're going to move on to a different aspect of design, which is visual design. How do we create visual designs? We're going to spend the next 3 lectures on this, more or less. And when we talk about visual design, we are going to spend a lot of time talking about this book and this author. This is The Visual Display of Quantitative Information by Edward Tufte. I will pass the book along. You can just sort of leaf through it. There's some beautiful illustrations. Tufte is kind of the godfather of visual design, about how to take a lot of data, turn it into, in some cases, pretty pictures, but most importantly, pictures that tell a story. Tufte was the one that came up with this phrase of maximizing the data to ink ratio, right? We're trying to visualize as much as we can about the behavior of our kNN learner using as little ink as possible. Okay, I'll pass. When you've had a chance to have a quick look at the book, pass it along. Might not get through everyone today. I'll bring it back on Thursday. Okay, so let's go back to lecture 5 for a moment. We were talking about design principles here, and like the last few lectures in HCI, we tend to have a lot of vague language. We want things to be usable, accessible, everyone should be able to use it, it should be intuitive, and so on. And we've been spending a lot of time taking those vague words and unpacking them into more words, but hopefully they're more specific words, and most importantly, they're measurable words. They're things that we can actually start to quantify, and we'll talk about quantification in a little while, right? So we want our system to be flexible, for example. That's a pretty vague term. What do we mean by that? Well, flexible in the sense that we allow a lot of different paths from A, which is where I am, to B, which is where I want to be. And B might be having a kNN learner that's much better than chance. That's where I'm trying to get. And a system might provide lots of different paths to get there. So now I can start to measure something. How many different paths, how many different ways are there for me to navigate from A to B? In the simple case of navigating on the web, there may be lots of different ways to get from where I am to a particular web page, and I can measure how many paths. For each of those paths, how many links do I have to click on to get there? That's, again, something that I can measure. I can start to boil things down into actual numbers. How long, in seconds, does it take a user to get from A to B along a particular path? How long in seconds, on average, does it take 100 of my users to get from point A to point B on a particular path, right? So we've gone from something that's very vague, flexible, to something that's very quantitative. That's, again, part of the black art of HCI, and we're going to come back to talking about measurement in a little bit. Okay, we ended last time with this sort of tongue-in-cheek example of polite software, right? You'll notice when people work with computers, you probably noticed yourself do this, you tend to anthropomorphize a lot. Your computer's being rude. It's nervous when somebody looks at the screen, especially when your instructor or the TA looks at the screen. Nothing's working at home. You bring it into office hours, everything works fine, right? Your computer's nervous in front of other people. It behaves. The minute you take it home, it misbehaves again, right? We tend to anthropomorphize. That's actually a good clue when people are testing a system, is to pay attention to the kind of language they use. Okay, we're a little bit behind where I want to be at this point in the course, so I'm going to skip over the next few slides. This is something you can sort of do on your own. Here are the 12 design principles that we talked about in this lecture, and you can write down websites, apps, devices like Leap Motion, examples of things where these 12 design principles are instantiated well or poorly. I'll leave that for you as an exercise for later. Okay, so let's switch now to lecture 6. Now we're going to focus specifically on visual design. Why are we talking about visual design? Because we are now in the age of big data. We are all drowning in data. There's more and more data being generated all the time, and basically society can't keep up. Think about all the data that's being generated at the hospital across the way today, right? There is a vast amount of data that is being collected but is not being analyzed and used for positive health outcomes. Some data is being collected, but a lot is being lost, right? As we saw even with the iris data set, if we have more features, our algorithm is better at predicting iris species. Could also be used to collect patient data and predict the efficacy of different drugs or different regimens towards health, right? That's why this is so important, right? We're learning as a species that the more we can measure, and if we team that data up with the right AI and the right human experts, the better we can do at solving problems. So where does visual design come in? Well, like you just saw for Deliverable 4, one of the first things we want to do as we start to collect data is find some way to visualize it and start to understand the basic structure in that data. And once we start to understand that basic structure, then we can start to apply AI and machine learning. Okay, what does big data mean? It means lots of different things to different people, but data is increasing in lots of different ways. First of all, the sheer amount of it. Many different classes of data. It comes in different forms. For example, floats and ints, that's a simple example. Data is stored at different time resolutions. In Leap Motion, for some of you, this might be the first time that you've written code that deals with data that's arriving at real time, right? That data is coming, and if you don't collect it fast enough, it's actually lost, right? Some of you might have been playing a fair bit with the pause at the end of your infinite loop. That matters. There's certain issues that come up when you're dealing with real-time data. Spatial resolutions, are we talking about mapping, GPS, autonomous cars? Are we measuring across inches at the atomic scale, square mile, parsecs, light years? What are we talking about? We're now, as a species, collecting data at lots of different spatial and temporal resolutions. We have subjective data, right? We have the world of social media. I know that you said that she thinks that he feels, right? That may or may not be important. Objective data, right? Are we measuring things that actually have, that we can go back and verify, something that really exists in reality? Data of doubtful quality. You've already noticed on leap motion that leap motion is not perfect. How do we deal with that situation? How do we deal with the noise that's in data? How do we know how much noise that's in there? We just saw that it matters, right? Picking this number makes a kNN algorithm more or less resistant to noise in the data. Okay, conceptual data. Are we deriving a number that has no direct correlation in reality, right? It's a measure of a concept or an abstract idea, or alternatively, the data has some physical counterpart. We're counting things, we can count them again. Metadata is an interesting one, which is data about data, right? So why is metadata important? Well, we can take, for example, Twitter data, and you can measure the data, the actual alphanumeric string of a particular tweet. Turns out now that for any individual tweet, the amount of metadata swamps the amount of data itself. So it's no longer 140 characters, right? It's, what is it, 280 now? Lost track. Nobody tweets anymore?
Like 280.
280. All right, let's say 280 characters, right? You can then ask, how many people have seen this tweet? How many people have clicked on the link? Who's seen it? Are there links to those people? And so on. So the cloud of data around those 280 characters has grown over the lifetime of the Twitter application. So what? Who cares? Well, if the amount of data is increasing, the number of tweets worldwide per day is increasing, and the ratio of data to metadata is increasing. So the Twitter company collects more and more metadata around an individual tweet, which is fixed at 280 characters. We have exponential growth, right? We have more tweets and more metadata about any individual tweet. So part of the problem with big data or the data flood is metadata. It's not the actual data itself. So we're not just talking about more data, but data is growing in different ways that produces different challenges. Why is there more data? Well, again, this one's kind of obvious, but related to this idea, big data is the Internet of Things. So we have probably about 30 or 40 of these in here. Some of you might be wearing a Fitbit. Some of you might have a cochlear implant. There are more and more devices in this classroom every year I teach this class. How many more? Well, it turns out that the Internet of Things, at least for now in the foreseeable future, is increasing exponentially. I apologize about the quality of this picture. Where are we here? Here's 2004, 2002, 2006, 8, 10, 12, 14, 16, 18. So we're currently there. This picture is from a couple of years ago. I think this is more or less accurate. There are now way more devices on the planet than there are people, and that is likely to increase. What is a device, or what is a thing in the Internet of Things? It's something that's connected to the internet, and it's usually supplying data, right? Your Fitbit is supplying information back to your phone or your laptop. We're pulling data off all of these things. The amount of data we're pulling off these things is increasing. The number of things themselves is increasing exponentially. Even the cloud, which is where most of all of this data is being stored, the cloud itself is not growing this fast. So demand, which are the devices that are trying to offload their data, is growing exponentially, and supply, which is the cloud, which is also growing. It's growing pretty fast, but it's not growing this fast. It means we have a problem. Demand is outstripping supply. So what do? Not a lot of people know, but first of all, we need to decide. Well, we don't know what we can do, but basically we can't keep all the data, right? We've got to throw some of the data away. Which data should we keep and which data should we discard? We need some way of visualizing and understanding that data. So every day at the hospital here, there's vast amounts of data that's collected, and someone somewhere in the hospital is deciding to discard some of that data. did they discard the right fraction? Right? How do we know? Okay, so that's what we're trying to help with in HCI. Just as another example here, here's an example of visual design. Some of you may have seen this picture before. What is this?
Oh, that's the.
You're measuring happiness of Twitter tweets based on keywords and things.
That's right. So we're measuring the happiness of Twitter. How could you measure the happiness of Twitter? Talk about that in a moment. We're back to subjective data.
They had a whole bunch of people like rate the happiness of various words, and they scan for those words in tweets and average the happiness.
That's it. That's the basic idea. We'll go over that. So this is the Madonna Meter. A meter, or a way to try and quantify hedonimy, or the amount of pleasure or happiness. This is reported happiness, right? Somebody wrote a tweet saying, I'm feeling triumphant today. Whether they actually are or not, hard to measure. So just keep that in mind. We're not really measuring the happiness of people on Twitter. We're measuring the self-reported happiness of people on Twitter. Okay, this is a research project helmed by Professor Dodds and Professor Danforth in the math department. Some of you may have taken classes from them. You can ask them about it. They can explain this much better than I can, but I think we had a great summary here. It turns out that for words in any language, including the English language, you can take a particular word, put it in front of a bunch of people, and ask them to measure the affect of that word. So affect is yet another term from psychology that we're going to see in this course. Affect is sort of the emotional content of that word. So if I gave you a particular word, like apple, and asked you to give me a score between 10 and minus 10, which is how happy or sad that word is, what score would you give to the word apple?
2, 5.
2, 5, 10. Somebody really likes apples. That's great. Okay. So we would take all of those scores and squash them down to a particular value. I can't remember what the range is here, but you sort of get the idea. If I give you the word suicidal, what is the affect of the word suicidal?
-6.
-6, -8, -10. It used to be the most negative word in the English language. I'm not sure if that's still the case. And triumphant is, again, used to be the word that got the highest positive affect of all words in the English language. So there's an actual data set of 10,000 English words, and for each of those 10,000 words, there's a number associated with it, which is the affect of that word. Given that data set, Professor Dodds and Danforth and their students receive every day a random collection of 10% of all tweets issued for that day. It's called the garden hose. So Twitter supplies the garden hose, which is 10% of all tweets every day, come here to UVM, and then in that data set, they trawl through all of those tweets looking for those 10,000 affect tagged words. Take all of those affect tagged words that are pulled out of the garden hose for that day, take those affect scores and average them across all the words for that day, which collapses down to a single number for a single day, which is the average happiness on Twitter for that particular day. There's also the fire hose, which is 100% of all tweets every day. Obviously, Twitter has access to the fire hose. We do not have access to the fire hose. There are certain three-letter acronym institutions in this country that have access to the fire hose. You can probably guess what those are. Okay, that's the data set. Here's the visualization that Dodds and Danforth came up with. And again, I like to show this because it's a great example of maximizing the data to ink ratio. What can you learn about self-reported happiness on Twitter over the last 10 years or so?
I think it's interesting that it's pretty consistent that Friday and Saturday are higher than the rest of the days. You see red at the top and the cooler colors, which represent the weekdays at the bottom of the
Makes sense, right? People tend to tweet happy words on Friday and Saturday more often.
It's cyclical.
It's cyclical, right? So we just talked about how data has different timescales in it. I'm not an expert in this area. I don't know if that was known beforehand, but there seems to be some sort of very low frequency, multi-year oscillation or change going on in the data set. I'm not sure if Dodds and Danforth and their students have a good answer to this. People don't like election year, so that's a good one. I hadn't noticed that one before. That makes sense. That could explain it, or explain part of this low frequency oscillation. Yep.
I could tell you exactly when Christmas fell in every single one of those years.
Ah, you can tell exactly where Christmas is. You stole my next question, right? What are these regular spikes you see every year? People self-report happiness around Christmas. What else? You'll notice a bunch of negative spikes as well, but they don't have a regular frequency, whereas most positive spikes do, which is interesting. Again, that's telling us something about the structure of this data set. Why is that the case?
It probably reads in from like holidays as positive events. People are like happy holidays or whatever it is.
Yep.
And then for negative events, whether it be like natural disasters or shootings or something, those are less predictable.
Absolutely, right? So unfortunately, disasters happen, and unfortunately they don't happen on a regular time scale that we can predict, right? Makes sense. You'll notice that for the positive spikes that happen around Christmas, there is also a smaller spike just before it. What is that smaller spike? Not Christmas Eve. Christmas Eve is on there, but it's right up against the spike.
Christmas vacation.
Not quite. Getting closer.
Thanksgiving.
Thanksgiving, right?
Wait, is this just American?
Ah, right? So already we're starting to learn something about now the demographics of those that tweet. There is a very strong spike at not Thanksgiving, but American Thanksgiving. I'm Canadian. Unfortunately, you can't see the Canadian Thanksgiving spike. Thank you very much. So at least the vast majority of people in this data set, and generally true of Twitter, tend to be Americans. So we can see, again, there's a certain bias or skew towards a certain demographic. You'll notice that the Madonna Meter is interactive, and this is important. We're going to talk about this later, so you can actually go and play with the data and actually see what happened during some of these periods. This is an important issue that we're going to talk about in this lecture, which is when we're talking about visualizations, visual design. Usually in HCI, it's not creating a static graphic for a book. We're usually creating a website or an app where we're going to assume that people interact with the visualization. This is going to be a conversation between users and the visualization. Okay, we'll come back to that later. Okay, so let's start to actually think about how to do this, right? I've shown you a few examples now of visualizations that try to maximize the data to ink ratio. Let's think about some design principles, which we talked about last time, kind of rules of thumb about how to create good visualizations. Okay, Edward Tufte, again, the author of the book that's going around, said we could try and simplify all the data and get it all sort of in the same format, which is fine. That helps us with visualizing it. But again, that's making our jobs easier as designers rather than focusing on what people want to do with the data. We want to put people first. So we might simplify, we might systematize a little bit, but when we do that, we're usually throwing away some of the data. We're averaging or dropping out some of the data. We're losing stuff. So we want to keep that in mind. Can we try and provide all the data as is? So visualize every single tweet, every single affect tagged word? Probably not. There's just too much data. So we can't do that because there's too much data and we would just have too much ink. If we were to try and alter this visualization to present everything, you would never have been able to do what you were trying to do, which is infer something about the structure of this data set. You would never have realized that this is mostly tweets from Americans. Okay, for example. So we're always trying to play this game in visual design between these two poles of simplifying things and trying to present as true a picture as possible. One good thing to do sort of in the middle, which we've already seen many times now, is provide a metaphor somehow, right? So the self-reported happiness of tweeters tends to go up and down over the years, right? And our visualization literally goes up and down over the years. There's yet another visual metaphor. Remember that when we're creating these visual metaphors, we're doing them in such a way that people can easily and probably subconsciously transfer their intuitions from the real world to the visualization, right? So let's try and create some visual metaphors here for the spread of things. How might you visualize the spread of AIDS around the world in the 80s and 90s?
You could have like a world map, and then
Okay.
For each year, maybe have a different color, and then the brightness or darkness of that color is based on the number of cases in the country that it's been colored in.
Okay, that's a great suggestion. Most people, when asked this question, come back with the map, right? Most people want to see where and when. So we have a world map, and as you were mentioning, maybe we have some color that spreads across the world map. Maybe the density or the shade of that color represents the density of AIDS cases in that particular part of the world. And then like Madonna Meter or Gapminder, maybe we include a slider bar, some sort of animation, so we can see how the spread changes over time, right? Most people converge on those subsets of visual metaphors. How about the spread of a meme? Very different from a disease, but it also spreads.
Yeah, but you can visualize it in the same way.
Exactly, right? So now we're not relying on somebody's ability to transfer intuitions from the physical world to the real world, but to transfer their intuitions about a visualization of something to a visualization of something that's similar, right? A meme and a disease are not really on the surface very similar, except they spread, right? And could we use the same visualization for that idea? Okay. We got to be careful, though, again, because not everyone will get the metaphor. Question or comment?
When you have to like include different things for the meme as it changes.
Maybe, right? So what is it that we're actually trying to project in this visualization, right? Is there some difference between a disease and an idea that require a change in the visualization? Maybe. Those are the right kinds of questions we want to ask. What is someone trying to get out of this visualization? Okay. Okay, we're going to, in a moment, we're going to watch the first part of a TED Talk, and this is a TED Talk by Hans Rosling, the creator of Gapminder. You might remember we talked a little bit about Gapminder at the beginning of the course. There's a number of TED Talks from Professor Rosling online now. We're going to go back and watch the first one, way back in 2004. And the reason why is there was a lot of stir around this particular TED Talk at the time, because back in 2004, it was very novel to present a visualization that presented structure in a large data set to a wide audience. Today, this might seem kind of obvious, but this was sort of the start of it. When we watch this TED Talk, I want you to literally write down a few notes as we go, because there are a lot of concepts in this 20-minute TED Talk that we've already covered. I want you to look or pay attention to all of the different concepts that Rosling talks about in these 20 minutes. Some of these things, again, are sort of concrete, like the number of AIDS cases, people actually suffering from AIDS. Others are more abstract concepts like gross national products, education issues. So what are the things that are being visualized? And then, how does Gapminder visualize those things, right? So what sorts of basic visualizations are shown, graphs and animations? What visual constructs are used to represent it? Circles, areas, heights, shading, opacity, animations, slider bars, and so on. And in this 20-minute talk, Rosling is going to use a lot of visual metaphors, and you'll know it's a metaphor because of the language he uses. So at one point, he's going to show you a wealth and health visualization and show how the rates of change of those two indicators change over time for two countries. And you can see that China is closing in on the US. There's a metaphor that he uses. Okay. You'll notice that he engages the crowd quite a bit. Remember our discussion about users and stakeholders. So who's involved in this 20-minute presentation? Okay, give me a moment to make sure I can get the audio working as well. Let's see if this works. Okay, and true to form, you cannot hear this very well.
Took on the task to teach global development to Swedish undergraduate students. That was after having spent about 20 years
Can those in the back hear okay?
together with African institutions studying hunger in Africa. So I was sort of expected to know a little about the world. And I started in our medical university, Karolinska Institute, an undergraduate course called Global Health. But when you get that opportunity, you get a little nervous. I thought these students coming to us actually have the highest grade you can get in Swedish college system. So I thought maybe they know everything I'm going to teach them about. So I did a pre-test when they came. And one of the questions from which I learned a lot was this one: which country has the highest child mortality of these 5 pairs? And I put them together so that in each pair of country, one has twice the child mortality of the other. And this means that it's much bigger the difference than the uncertainty of the data. I won't put you at a test here, but it's Turkey, which is highest there, Poland, Russia, Pakistan, and South Africa. And these were the results of the Swedish students. I did it so I got a confidence interval, which was pretty narrow, and I got happy, of course. I had 1.8 right answer out of 5 possible. That means that there was a place for a professor of international health and for my course. But one late night, when I was compiling the report, I really realized my discovery. I have shown that Swedish top students know statistically significantly less about the world than the chimpanzees. Because the chimpanzee would score half right. If I gave them 2 bananas with Sri Lanka and Turkey, they would be right half of the cases. But the students are not there. The problem for me was not ignorance, it was preconceived ideas. I did also an unethical study of the professors of the Karolinska Institute that hands out the Nobel Prize in medicine, and they are on par with the chimpanzee there. So this is where I realized that there was really a need to communicate, because the data of what's happening in the world and the child health of every country is very well aware. So we did this software which displays it like this. Every bubble here is a country. This country over here is China. And this is India. The size of the bubble is the population. And on this axis here, I put fertility rate. Because my students, what they said when they looked upon the world, and I asked them, what do you really think about the world? Huh? Well, I first discovered that the textbook was Tintin mainly. And they said the world is still we and them. And we is Western world, and them is third world. And what do you mean with Western world? I said, well, that's long life in small family, and third world is short life in large family. So this is what I could display here. I put fertility rate here, number of children per woman, 1, 2, 3, 4, up to about 8 children per woman. We have very good data since 1962, 1960 about, on the size of families in all countries. The error margin is narrow. Here I put life expectancy at birth, from 30 years in some countries up to about 70 years. And 1962, there was really a group of countries here that was industrialized countries, and they had small families and long lives. And these were the developing countries. They had large families and they had relatively short lives. Now, what has happened since 1962? We want to see the change. Are the students right? It's still 2 types of countries? Or have these developing countries got smaller families and they live here? Or have they got longer lives and live up there? Let's see. We stop the world. And this is all UN statistic that has been available. Here we go. Can you see there? It's China. They're moving against better health. They're improving there. All the green Latin American countries, they are moving towards smaller families. The yellow ones here are the Arabic countries, and they get larger families, but longer life, but not larger families. The Africans are the green down here. They still remain here. This is India. Indonesia is moving on pretty fast. And in the 80s here, you have Bangladesh still among the African countries there. But now Bangladesh, it's a miracle that happens in the 80s. The imams start to promote family planning, and they move up into that corner. And in 90s, we have the terrible HIV epidemic that takes down the life expectancy of the African countries, and all the rest of the world moves up into the corner where we have long lives and small family, and we have a completely new world. Let me make a comparison directly between United States of America and Vietnam, 1964. America had small families and long life. Vietnam had large families and short lives. And this is what happens. The data during the war indicate that even with all the death, there was an improvement of life expectancy. By the end of the year, the family planning started in Vietnam, and they went for smaller families. And the United States up there is getting for longer life, keeping family size. And in the 80s now, they give up communist planning and they go for market economy, and it moves faster even in social life. And today we have in Vietnam the same life expectancy and the same family size here in Vietnam 2003 as in United States 1974 by the end of the war. I think we all, if we don't look in the data, we underestimate the tremendous change in Asia, which was in social change before we saw the economical change. So let's move over to another way here in which we could display the distribution in the world of the income. This is the world distribution of income of people. $1, $10, or $100 per day. There's no gap between rich and poor any longer. This is a myth. There's a little hump here. But there are people all the way. And if we look where the income ends up, the income, this is 100% of world's annual income. And the richest 20%, they take out of that about 74%. And the poorest 20%, they take about 2%. And this shows that the concept developing countries is extremely doubtful. We sort of think about aid, like these people here giving aid to these people here. But in the middle, we have most of the world population, and they have now 24% of the income. We heard it in other forms. And who are these? Where are the different countries? I can show you Africa. This is Africa. 10% of the world population, most in poverty. This is OECD, the rich country, the country club of the UN. And they are over here on this side, and quite an overlap between Africa and OECD. And this is Latin America. It has everything on this earth, from the poorest to the richest in Latin America. And on top of that, we can put East Europe, we can put East Asia, and we put South Asia. And how did it look like if we go back in time to about 1970? Then there was more of a hump. And we have most who lived in absolute poverty were Asians. The problem in the world was the poverty in Asia. And if I now let the world move forward, you will see that while population increase, there are hundreds of millions in Asia getting out of poverty, and some others get into poverty. And this is the pattern we have today. And the best projection from the World Bank is that this will happen. And we will not have a divided world. We will have most people in the middle. Of course, it's a logarithmic scale here. But our concept of economy is growth with percent. We look upon it as a possibility of percentage increase. If I change these and I take GDP per capita instead of family income, and I turn these individual data into regional data of gross domestic product, and I take the regions down here, the size of the bubble is still the population, and you have the OECD there, and you have sub-Saharan Africa there, and we take off the Arab states there, coming both from Africa and from Asia, and we put them separately, and we can expand this axis, and I can give it a new dimension here by adding the social values there, child survival. Now I have money on that axis, and I have the possibility of children to survive there. In some countries, 99.7% of children survive to 5 years of age, others only 70. And here it seems that there is a gap between OECD, Latin America, East Europe, East Asia, Arab states, South Asia, and Sub-Saharan Africa. The linearity is very strong between child survival and money. But let me split Sub-Saharan Africa. Health is there, and better health is up there. I can go here, and I can split Sub-Saharan Africa into its countries. And when it bursts, the size of each country bubble is the size of the population. Sierra Leone down there, Mauritius up there. Mauritius was the first country to get away with trade barriers, and they could sell their sugar, they could sell their textiles on equal terms as the people in Europe and North America. There's a huge difference between Africa, and Ghana is here in the middle. In Sierra Leone, humanitarian aid. Here in Uganda, development aid. Here, time to invest. There you can go for holiday. It's a tremendous variation within Africa, which we very often make that it's equal everything. I can split South Asia here. India is the big bubble in the middle, but huge difference between Afghanistan and Sri Lanka. And I can split Arab states. How are they? Same climate, same culture, same religion, huge difference. Even between neighbors. Yemen, civil war, United Arab Emirates money, which was quite equally and well used. Not as the myth is. And that includes all the children of the foreign workers who are in the country. Data is often better than you think. Many people say that data is bad. There is an uncertainty margin. But we can see the difference here, Cambodia, Singapore. The differences are much bigger than the weakness of the data. East Europe, Soviet economy for a long time, but they come out after 10 years very, very differently. And there is Latin America. Today we don't have to go to Cuba to find a healthy country in Latin America. Chile will have a lower child mortality than Cuba within some few years from now. And here we have high-income countries in OECD, and we get the whole pattern here of the world, which is more or less like this. And if we look at it, how it looks the world, in 1960, it starts to move, 1960. This is Mao Zedong. He brought health to China. And then he died, and then Deng Xiaoping came and brought money to China and brought them into the mainstream again. And we have seen how countries move in different directions like this. So it's sort of difficult to get an example country which shows the pattern of the world. But I would like to bring you back to about here at 1960, and I would like to compare South Korea, which is this one, with Brazil, which is this one. The label went away for me here. And I would like to compare Uganda, which is there. And I can run it forward like this. And you can see how South Korea is making a very, very fast advancement, whereas Brazil is much slower. And if we move back again here, and we put on trails on them like this, you can see again that the speed of development is very, very different. And the countries are moving more or less in the same rate as money and health. But it seems you can move much faster if you are healthy first than if you are wealthy first. And to show that, you can put on the way of United Arab Emirates. They came from here. A mineral country. They catch all the oil, they got all the money, but health cannot be bought at the supermarket. You have to invest in health. You have to get kids into schooling. You have to train health staff. You have to educate the population. And Sheikh Zayed did that in a fairly good way. And in spite of falling oil prices, he brought this country up here. So we got a much more mainstream appearance of the world, where all countries tend to use their money better than they used in the past. Now, this is more or less if you look at average data of the countries. They are like this. Now, that's dangerous to use average data because there's such a lot of difference within countries. So if I go and look here, we can see that Uganda, that today is where South Korea was 1960. If I split Uganda, there's quite a difference within Uganda. These are the quintiles of Uganda. The richest 20% of Ugandans are there. The poorest are down there. If I split South Africa, it's like this. And if I go down and look at Niger, where there was such a terrible famine, lastly, it's like this. The 20% poorest of Niger is out here, and the 20% richest of South Africa is there. And yet, we tend to discuss on what solutions there should be in Africa. Everything in this world exists in Africa. And you can't discuss universal access to HIV for that quintile up here with the same strategy as down here. The improvement of the world must be highly contextualized. And it's not relevant to have it on regional level. We must be much more detailed. We find that students get very excited when they can use this. And even more policymakers and the corporate sectors would like to see see how the world is changing. Now, why doesn't this take place? Why are we not using the data we have?
Okay, I think we'll pick it up there next time. You have a quiz due tonight. You have an extension on Deliverable 3, and you can get started on Deliverable 4. See you on Thursday.